This is second independent variable and the error term. This is our population regression model. Okay. Now I suppose this is consumption expenditure again. Okay. Your first explanatory variable is income, same as earlier, but now we add wealth as additional variable in the model. We add wealth as additional variable in the model. Now, what would be the problem in this estimation? Can someone just guess about it? If
Wealth and income,
what will happen between them?
they are correlated.
They are correlated, exactly. So the problem of multicollinearity is nothing but there is correlation between independent variables. So one of the assumptions that we make when we go for multiple linear regression, this is the case of multiple linear regression. Okay. One of the assumptions that we make is that there is no perfect collinearity. The assumption is that there is no perfect collinearity. What do you mean by this? Can someone explain? No perfect collinearity. This is the assumption we make while estimating multiple linear regression model. It implies that the correlation between someone is saying something.
Yeah, there is absence of correlation between or among the independent variables.
When I say no perfect correlation, what do you mean no perfect? The correlation coefficient will be equal to 1 if it is a perfect collinearity. So when I say no perfect correlation, I mean that there is a correlation between x1 and x2, but it is not perfect. It is not equal to 1. It is very high, say around 0.85, or it could be 0.90. It is very high, but not perfect. This is okay for estimation of beta 1, beta 2, and alpha. But if you have perfect correlation between x1 and x2, you cannot estimate alpha, beta 1, beta 2. So they are called as indeterminate. You cannot actually determine the values for those when correlation coefficient between x1 and x2 is equal to 1. But if it is less than 1, still you can go ahead with the estimation. You estimate alpha hat, you calculate alpha hat, you calculate beta hat 1, you calculate beta hat 2. But the problem with such kind of multicollinearity, that is high correlation between independent variables, is that the variance of these estimators will be very high. Variances of the standard errors of estimators will be very high. Okay. So if the standard error of the variances are high, the precision of the estimation will be less. When this kind of problem actually occurs in the regression, your OLS estimators beta hat 1, beta hat 2, alpha hat will continue to be unbiased. They will continue to be efficient. They will continue to be linear. They will continue to be consistent. But the only problem is that they will have large standard errors. The only problem when there is a high multicollinearity, we are going ahead with high multicollinearity, not the perfect multicollinearity. We are moving ahead with high multicollinearity. Then the standard error will be variances of the standard errors of the estimators will be large. And what would be the implications of these large standard errors in hypothesis testing? How do we test for the hypothesis? How do we construct the test? Beta hat 1 upon standard error of beta hat 1. If this is very high, what will happen to t?
Small.
T will be small. So you will get insignificant coefficients from this kind of regression model. Even though there is some actual relationship between those variables, due to multicollinearity, from the statistical test, of hypothesis of beta hat 1 is equal to 0 and it is not equal to 0, your t value will be less and it will indicate that the coefficient is insignificant. Understood? So this is one implication on the test statistic, t-test statistic in hypothesis testing when there is multicollinearity, because you have large standard errors of this regression coefficients. Okay, so this is the problem that we actually encounter. And how do we denote the variance formula now? Suppose you are writing variance formula for beta hat 1, it will be sigma square E upon summation xi1 minus x bar 1 into 1 upon 1 minus r square 1 2. Now what is r over here?
Coefficient between x1 and x2.
What coefficient?
Correlation between.
It is correlation coefficient, isn't it? So it is squared correlation coefficient between x1 and x2, and it is called as r square. You must have heard about this term. Right? So this is how we write the formula for variance of beta hat 1. What would be the formula for variance of beta hat 2? Just following this earlier formula, xi2 minus x bar 2. Sorry, this is square. I just forgot to write square here. It is square. Summation xi minus x bar square. Summation xi minus x bar square into 1 upon 1 minus r square, the correlation coefficient squared for x1 and x2. Now this second term, understand, this second term is actually called as variance inflation factor. Variance inflation factor, VIF. What does this mean? It means that it gives you the value by which the variance of beta hat, sorry, this is 2, beta hat 2. It gives you the value by which the variance of beta hat 2 is actually inflated due to correlation between x1 and x2. So this is the original variance formula. But due to multicollinearity, we have this additional term, variance inflation factor, and it indicates that by what quantity or by what magnitude the variance of beta hat 1 and beta hat 2 has been inflated because of the correlation between x1 and x2. Okay, if this term is very high, what will happen to the variance of beta hat 1 and beta hat 2? If the variance inflation factor is high, variance of beta hat 1 and beta hat 2 will also be high. But when will variance inflation factor be high?
And the correlation between correlation coefficient R1
Right.
2 will be
Is very high.
high.
Exactly. So when correlation coefficient is very high between x1 and x2, that is, this term is very high. This term is very high. This numerator denominator will be very low. High numerator divided by low denominator will give you the high term, very high ratio of these two. And if you multiply this high value with this term, you will get high variance of these two. Understood? So you can explore this. I won't spend much time on this. So what we do actually in regression model, suppose you have multiple variables in your regression model as independent variable, and you suspect that there is possibility of collinearity of the exact linear relationship between independent variables, you look at variance inflation factor. Okay. Normally, the variance inflation factor in excess of 5 or in excess of 10 is considered as a serious problem. So now let's go to R. Have you received the file from sir?
Yes.
So there is one CSV file for multicollinearity. Can you see that?
Yes.
Yes,
please
yes.
please download that. We will read that as data one over here. Read.csv. Save that file somewhere at desktop or anywhere you want. File.choose. Comma. Header is equal to true. So we are asking R to create the first row as a name of the columns. So just have you received that script also? R script.
Yes, we have received.
Yes,
Please, so please open that from go to file, open file, and go to the place where you have saved that R script. So the moment I click on this, the small window will open. Can you see the window is opened? So in your case, you'll have to go to the folder or the place where you have saved that multicollinearity file. So I click on that file, which I want to read over here, and just open it in R. So this data one, I type head data one. These are the variables that we are including in our model. Have you loaded the data? Yes. What about others? Everybody's done that? Please tell me once you are done.
Just a moment, sir.
Yeah, sure. Are you done? Can we move ahead? So if you see that in this data set, there are total 4 variables. One dependent variable called as femoral.neck. Now this data is not from our field; it is from medical field. Okay, but to make you understand the problem of multicollinearity, there is very good. This is very good data set that actually give you more insights regarding this problem. So it is femoral.neck. Now, what is femoral.neck? It is nothing but the bone mineral density of the femoral neck. Okay. So I have described this data over here. If you open that script, you will understand. Have you opened that script? So there is a description of these variables. The variables are physical activity, body fat percentage, weight, and then bone mineral density of the femoral neck. Now I run the regression using this variable, and my dependent variable is femoral.neck from my data which is loaded. So I run this model. So I run this model. We see that femoral.neck is my dependent variable regressed on fat x.fat plus weight.kg activity into plus fat.weight
Post it in the chat also.
Sure, I'll do that.
The code is posted in the group. Multivariate VIF code is posted in the group. The one that Dr. Bhavesh has shared.
Please use those codes and try to run that regression model. So our last variable is the interaction term. If you open the Excel, the CSV file, you will understand that the last column is the interaction term, interaction between fat and weight after activity. So let's move to the estimation part. We estimate this regression model. This is the summary of the model. And if you see that almost all variables except fat are significant in the model, they are impacting the bone density of people. Do you suspect that there is a possibility of multicollinearity in this regression model? What do you think?
Yes.
Oh, in which variables? Now we have 4 variables.
Activity, weight,
Exactly. Yeah. Then
even
fat, weight,
fat, weight,
fat activity.
fat, and all the fat.
In fact, yeah. So in fact, your 1x variable, say for example, weight, is actually correlated with number of things like activity, fat, right? So there are 2 variables which are actually correlated with activity, correlated with weight. Similarly with other variables. So here, what we actually having is this. Your x1, say for example, any x1, say for example, weight, is actually correlated with x2 and x3 and x4, say, if there is 4th variable. Now, since it is correlated with all these 3, the R square that we have actually calculated in the simple linear, in case of 2 variable case, will now be what? R square with the subscript j for jth variable. Now j is going from 1 to 4. So if you want to calculate the correlation coefficient of the R square for regressing x1 on the remaining variables, you will denote that as maybe with the capital R, since we have more variables. So R square j is for jth variable, j is going from 1 to 4, and it will be equal to R square from regression of x1 on x2 plus x3 plus x4. So you calculate, you regress this on this, calculate R square, and that R square will actually appear in the variance of beta hat 1 formula, which will be nothing but sigma square E upon summation xi minus x bar square upon 1 minus R square j. Now R square j is actually this R square. Now you will change the variable. You, instead of x1, you put x2 over here as j variable, and regress x2 on the remaining variables, regress x3 on remaining variables, and so on. Okay, so this is the variance of beta hat j. J is for jth variable, will give you this variance formula in the case of more than 2 multiple more than 2 independent variables in the model. So this is how we calculate variance of beta hat j, and this is now variance inflation factor. Now let's go to the variance inflation factor in R output. Let's calculate that. You need to install package car for that. So install.packages car. Use double inverted comma.
Sir, this error which you are getting now,
Sorry.
so this error which you're getting now, right? There was some loading and this package R is running. I got
It is in console. It is in console.
Yeah, in the console. So my console is entire red with the, when I was installing the first one, D player.
What was that error? If it is red, then there is some error. Or error or warning?
First is it is closed now. Wait, I'm in the next console.
Maybe now you focus on this. You don't
Yes,
waste time in going for that.
So do we need to rewrite the command? That is my question. If we get the error, so we need rewrite the command and continue?
You continue with the rewriting it. So my package is now downloaded. I load that package by putting library R. Okay. That package is being loaded. Now there is command called as VIF. I think V is capital. VIF, so not capital, it is small. Inside the bracket, which model we want to test for multicollinearity? M3. If you do this, the output is given. Now you tell me which is the serious problem in this output. Which variable is actually highly correlated with remaining variables? Fat weight is the interaction term. Just ignore this. From these three variables, activity, weight, and fat.
You mentioned that values of 5 or 10 and above are problems.
Yeah, it's
Fat
serious.
and
So
weight,
which
fat and weight.
fat and weight, exactly. So fat and weight are highly correlated with the other variables. Okay, and what is this value? 33.94. It is this value, R square Z. That is regressing fat. Sorry, that is regressing activity on fat, weight, and fat into weight. R square from that regression is regressing weight on activity, fat into weight, and fat is actually regressing that you get R square, and that R square is nothing but this value 33.94. R square from regressing weight on activity, fat, and fat into weight. Similarly, x dot fat 14.93 is the R square from regressing fat on weight, activity, and fat into weight. Okay, so ideally, what should we do? Should we omit these variables or let these variables be in the model? Because all the properties of OLS estimator are still satisfied even though there is multicollinearity. Only problem is that the standard errors are large, and therefore your t statistic is very low. If t statistic is very low, then probability of failing to reject the wrong null increases, because the test statistic will be insignificant. So even though the null is false, you may fail to reject that false null, isn't it? Your confidence interval will be very large. All these are the different implications of getting very large standard errors when there is multicollinearity. Is this clear, student? Is this clear, participant?
Sir, just a one question. This
Yeah.
VIF command,
Mhm.
okay, this exfact, weight, kg, activity, what these numbers are giving us?
These numbers are giving you the values of R square. R square, since we have multiple variables. My screen is why automatically closed? Just a minute. Give me one more. See what we have. This is the formula for the variance of beta hat j. We have calculated this value now with the help of that command. Now what is this value? 1 upon 1 minus R square j. Now what is R square j? When you talk about particular j coefficient, suppose you are talking about beta hat 1. Okay. Now how do we calculate R square for one first variable? You regress x1 on x2 plus x3 plus x4. Do this regression, get R square from this regression for first variable, and that R square is been put over here. Once R square is calculated, you calculate this value. Yes.
So is this model that we are now explaining is significant because the R square is too small?
You are talking about model or the multicollinearity results?
Sir, this VIP that the function we have run right now.
No, the VIP is just giving you the collinearity between variables, the variance inflation factor.
Sir, weight.kg 33.94 is the R square value, no?
Yes. This is the R square from regressing weight on the remaining variables, independent variables. So you are actually performing regression using independent variables. You are not using dependent variables. Please remember that.
Okay. So the fact is regress on the remaining variable. Weight is regress on the remaining variable.
Correct. And you calculate R square.
Yes, activity is regress on remaining variable. So in this case, the weight is more, R square is high, or the fat is regress on the remaining variables. Okay, sir.
Right. So these values are not R square. Students, participants, please understand. These values are actually VIA. And what is VIA? This term. 1 upon 1 minus R square j. So this whole term ka value is these values which are calculated over. Okay, these are the variance inflation factors. They are giving you by what magnitude inflated due to multicollinearity between among the independent variables. So weight ka variance actually inflated by 3.94. X fat ka coefficient is actually inflated by 14.93. And if you go to the standard errors, now see the standard errors for weight, activity, fat. Now these are the scientific notions. So it indicates 10 raised to minus 3. So shift 10 digits to the left from 4. So it will be 0.004. This will be 0.002 for weight. Activity it's too low. For fat weight, it is too low. For these two, it is high for fat and weight. But students understand that the variance inflation factor will not always lead to very high variance of beta coefficient. Why? Because the variance of beta coefficient is also depend on these two terms, sigma square, that is variance of error term, and the variation in that independent variable itself. So even though this is very high and this is counterbalanced by these two terms, variance should not variance of beta hat should not increase. So you have to keep these things in mind. I don't want to of variance of beta hat. So even though VIF is very high and it is counterbalanced by these two terms, it need not necessarily increase variance of beta hat. Okay. So by this statement, I think I will just quickly move to autocorrelation problem. Is that fine?
Yes. Yes.
Okay. So the last thing that we are going to talk about now is what do we mean by the problem of autocorrelation? So the problem of autocorrelation actually occurs in time series data. Now, what do we mean by time series data? I will use some economic terms over here. I use the India's GDP recorded from say 1996. It is the gross domestic product, that is the value of the output produced in the economy, going from 1996 to 2000. 2020. This is one variable. Say this is a variable Y. We have another variable that is, say, for example, inflation in the economy. And again, we have yearly data for inflation, and it is inflation is again have some values over here. So this is my inflation data, which is variable X. Okay. So now, when we have this kind of data set, there is a relationship between the subsequent values. If you see that if this GDP level is very high, say for example, this is 2019. If the GDP in 2019 is very high, it is more likely that the GDP in 2020 will be very high. Because we have now regression model like this, YT with the team subscript T, alpha plus beta XT plus AT. So now all the variables now actually having the subscript, which is the time subscript. So these variables are changing over time. Since they are changing over time, the value of that variable in the earlier period actually influence its value in the next period. Okay. So it is more likely that if the GDP in this period is very high, the next period GDP is very high. It is more likely that if GDP in this period is low, the GDP, that is gross domestic product, in the next period is likely to be low. Same with inflation. So the moment we have this kind of relationship in the data, where the time sequence matters, okay, we actually encounter the problem of autocorrelation. We encounter the problem of autocorrelation. So what do you mean by problem of autocorrelation? Suppose this is the regression model. This error term is actually determined by its previous value, that is value in the previous period, plus some white noise error term. Now this error term is having mean zero, constant variance, and all the remaining properties are satisfied by this VT. But here you have this coefficient rho that is called as the autocorrelation coefficient, and it tells you that by what magnitude the error term in the previous period actually influences the error term in the current period, that is in period T. If this value is significant, then there is a problem of first order autocorrelation. There is a problem of first order autocorrelation. Why first order autocorrelation? Because this error term AT is actually regressed on its immediate past value, that is AT minus 1. So we will stick to this simple AR1 process. This is called as AR1 process, autoregressive process of order 1, because it is actually regressed on its immediate past value, ET minus 1. We can have autoregressive process of order 2 as well, but let's stick to this simple AR1 process. Okay. Now, what happens actually, when this kind of a problem occurs in the regression, where the error terms are correlated. If ET is actually ET minus 1 is influencing ET, what will happen to YT? YT will also get influenced by ET minus 1. You understand the link? If you see the model, it is actually influencing YT, but it is influenced by ET minus 1, the error term in the previous period. So indirectly, it is actually influencing YT through ET. Sorry, ET minus 1 is influencing, because ET and ET minus 1 are correlated. I'm saying that it is influenced by ET minus 1. In our regression model, ET influences YT, dependent variable. But since ET is itself influenced by ET minus 1, and it is influencing YT, actually ET minus 1 is influencing YT through ET. So such kind of issue actually your regression, this thing, because of autocorrelation between ET and ET minus 1. And when this covariance between ET minus J is not equal to 0, we have the problem of autocorrelation, which implies that the errors are correlated with their own past values or the future values. Problem of autocorrelation. I just wanted to take you some graphical demonstration of this from the book. So maybe quickly I will do that. This is what happens actually when there is a correlation in the error terms. You will see that error terms are not randomly spread. There is some pattern in the error terms because they are correlated. All the positive errors are bunched together over here. All the negative errors are bunched together over here. So this is the case of positive autocorrelation. Positive error is followed by positive error in the next period. Okay, negative errors are followed by negative errors in the next period. The second plot is for the negative correlation. So the positive error in this period is followed by negative error in the next period. Negative error in the next period is followed by positive, and so on. So we get zigzag type of line, and it is correlation. And if you don't have any kind of pattern like this, and the error terms are just randomly spread, there is no any pattern, then you say that there is no correlation in regression model. There is no autocorrelation in the regression model. Okay. Now there is a test, formal test to actually look for this. For the first order autocorrelation, the test is called as Durbin-Watson test. We are going to use this test. Once you test for the autocorrelation, okay, if there is autocorrelation, you go for generalized least square estimator. You go for generalized least square estimation. Okay. And the problem of autocorrelation generally arises because the time series variables, they trend over time. So if you plot some variables, they will have graphs like this over time. This is year 1996. So 2007. If you see that GDP has increased over a period of time, inflation has also gone up over time. So both are trending. When we have this kind of trending variables and you do the regression using these variables, you get this Fourier's relation of the Fourier's regression, where you will have the problem of autocorrelation in the regression estimation. Let's go to the example. the implication of this, I think you can go to the book. The OLS estimator is still unbiased. It is consistent, but it is not efficient. So it does. You cannot guarantee that the OLS estimator is having a minimum variance. So variance formula is different under autocorrelation when there is autocorrelation in the regression model. Let's go to the R now. I have, I think, a couple of examples over here. Just we'll try to explore that. There is data set called as data HSEINV. I'm sorry, where did I lose the connection? Can you tell me?
You just told us about the data. Beyond that.
Data SHEC.
Okay, good. So just now I thought it's I lost the connection long back. So just yeah. So this is the data. I am picking up only two variables: LINVP and L.
Sorry, sir. Your screen is not shared.
Oh, sorry. I think we are a little delayed. Maybe another 5 minutes I'll take, and we'll finish this off. So I pick up two variables from this data set. Now, this data set, if you want to see what we have in this data, just use this help command. Click on this data. So this is the data on 42 observations on 14 variables. So we have real housing investment as INV. Then there is housing price index. LINV is the log real housing investment in $1 million, and L price is the log price, that is log housing price index. Okay, so these two variables we pick up from the data along with T. T is the time trend. So if you select this data by using this subset command, we have new data set, data 4, that includes only these two variables. I convert this data into time series data set as by using the command, using the function TS for time series. I am converting data 4 in time series starting from 1947 with the frequency 1. So this is yearly data. So I do that. Data 5 is now time series data. You can see the years from 1947 to 88. If I plot this data, you will see the interesting things over here. All the variables are trending. When they are trending, and since it is a time series data, definitely they are non-stationary variables. I don't want to go into details of stationarity, non-stationarity, but they are non-stationary because they are trending up. When you include those variables in the regression, I run the model called as M6, regressing log investment per capita on log price using data 5. My regression results are this. the coefficient is significant. Okay, now I take the residuals, that is array terms, out of this model. So use the function resid for that. So I get residuals. I try to plot residuals to see if there is any pattern in that indicates the autocorrelation. This is the plot I get. Do you think there is a possibility of autocorrelation? Is there any pattern in the residual? We are not sure. So let's go for the formal test. Unit library LM test. There is a test called as DW test, which is called as Durbin-Watson test. From this package LM test, we use that data. We use this test on the model M6 that we have just estimated. And if you see that, the test result indicates that P value is very low, DW is very close to 0. It indicates there is possibility of positive autocorrelation in the residuals. Okay. So now what I do, I try to difference this series. I take the first difference. So my model 8 actually talks about difference, that is first difference of variable 1, dependent variable, first difference of variable 2. I execute this, and interesting things will happen now. If you see that this is my model, if you see that the variable has become insignificant now, which was significant in the earlier case, which was wrong estimation basically. If you test for the DW test, now it will indicate there is no autocorrelation when we take the variables in difference format. So DW statistic is very close to 2, indicates that no autocorrelation, and P value is 0.21, indicates that we fail to reject the null hypothesis of no autocorrelation. There is one more example which is given in the script. You practice that at home. So this example is on inflation and unemployment, the Phillips curve phenomena that we study in economics. You can actually test that curve with the help of inflation and unemployment data and see whether there is autocorrelation in the regression model or not. So that data is also available in Ullrich package called as the data name is called as Phillips. In the Ullrich package, you can use that for the practice. I have provided you one extra data set on HDI rankings. Whatever we have done so far as far as heteroscedasticity multicollinearity is concerned, you please practice using that data set on HDI rankings. I think I'll stop here for today. Thank you so much for being patient and being interactive throughout this session on issues in regression model. Thank you so much. Is there any question?
Please ask questions if you have questions.
Sir, hello? Hello?
Yes.
Sir, can you please show us how you have downloaded this data HSEINV from Ullrich?
See, you will just have to use, you have to install, we have already installed Ullrich.
Yes.
Just type data inside the bracket, double inverted comma. What is the name of that data?
HSEINV.
So double inverted comma mein you put that name. Control enter. Sorry, I just made some mistake over here. So it
You
is,
already has given a script, sir.
so from there you can see it is HSEINV. I don't know why this is happening. Can you see it from the script? There is some problem
Yes.
with my this thing. At double inverted comma, now it is come. So this data you just run like this, okay, and you just again type HSEINV. The data will be shown. Okay.
Yes, sir. Yes, sir.
Okay.
It's coming. Okay.
So,
Yes.
if you have a time, just can you explain it the DW test here in the R last
See,
part?
see, the DW test statistic is this.
In R, sir. R.
I'll just show you the formula. You will understand it quickly. So DW is equal to 2 into 1 minus rho hat. Okay, I think I am correct. Now R may, if you go to R, this is the statistic we get from that test. Where is that? Yeah. There is some issue with my PC actually. हाँ, ये किया था ना? It was model 6, no, that we regressed.
Yes.
Yes. So run this. I don't know why is this happening. There is some error that is happening, and it is giving me something different when I execute the command. Maybe I'll have to shut down my session for that.
Sir, only show the commands you did for the DW test.
Yeah, the command is this. It is DW test inside the bracket M6. This is the model that we estimate, and on that model we perform the test.
Then we did the regression M7.
That is different, where I include the trend because we don't have time. I have not done that. If you include the trend in this regression, no, interestingly, this trend will become significant, and these two variables, this price variable will become insignificant. Okay, the moment you introduce trend, because these both variables are trending over a period of time. You can try this. This is very interesting example. You can explore this.
Sir?
Yes.
Hello. Sir, every time when you are giving a command to any function, you are keep changing the name of the result, like M3, M4, M5. So can you please explain why we are doing this and how we can get the result from the R output?
See, basically what we are doing by giving name M3, M4, we are creating an object in R. R is an object-oriented software. So once you create M3, you can give that again the same name to the next model. But if you by mistake you execute the first command as by mistake you execute the first model as the second model, there will be a problem if you are giving the same name for both the models. तो अगर मैंने M3 फर्स्ट एग्जीक्यूट किया एंड अगेन सेकंड मॉडल मैंने M3 नाम दे दिया, सो फर्स्ट यू एग्जीक्यूट M3 फर्स्ट वाला, उसके बाद यू विल गेट द रिजल्ट. The second you can give the same name, but there will be a confusion. Okay, because as you go further and you want to come back again for first or second model, you are not aware of exactly which output you are going to you want to see, and there will be a problem of that confusion. Only that problem is there to avoid confusion.
Okay, thank you, sir.
But it is better always to give different names to different models to avoid confusion.
Sir,
and
yes,
all
sir.
these objects are stored in the R memory. तो कभी-कभी क्या होता है कि R will give you the past outputs. If you press the same name M3, it will give you previous वाला M3.
So that is why I am asking that from where we can get this after after shut down the software. See, we want to see the previous or the last 2 days work or the M3 or M4 or M5. We are very much new in our software. So from where
Sure. Yeah, I got your point, and very interesting question you have asked. You can actually save this script. Okay. You can save this script as R file, store it somewhere, and suppose you want to again want to go through all these commands, you go to file, click on open file, this small window will open. go to the place where you have saved that file and click on that file and click on open. So this file will quickly be opened in RStudio. And you can have the same commands again, but you will have to execute all the commands again, except installing the packages, because packages are already installed.
So can we, sir, save the console again, like save as the console thing?
Yes, I think you can save that. When you try to close R, there is option for saving console as well.
Okay.
When you try
And
to close
for the script part, we only can save the command that we have given, or the packages that we have installed before, that will be keeping there, no?
Yes, everything will be there. Whatever you have typed in this screen, no, that will prevail. That will prevail. And next time also you can see all these things. Only thing is that you will have to use this library function again to load those packages.
Okay. Yes, sir. Yes.
Okay.
Sir. Thank you, sir.
Yeah.
So, and suppose now there are 4 or 5 scripts open.
Hmm.
So I want to save the script 4. So that individual file untitled 3, how I can save that?
You just click on that screen script, go to file,
Okay.
then go to save as,
Okay.
and give the name whatever you want and place it wherever you want.
Okay, thank you, sir. So that only individual file I can save.
Yeah, and it is better always to save all this work, whatever we have done.
Yes.
So just to avoid that loss of losing, problem of losing everything that we have done. So I think in RStudio it remains, but sometimes if there is some problem with R, it is not functioning well, it may disappear. So it is better to save it. Okay.
Thank you very much, sir.
Yeah,
Answering our queries very patient.
Thank you so much for cooperating and being patient throughout. Sir,
Any other questions?
Yeah, yes, sir.
Okay. Bhavesh, I guess you have also covered things like omitted variable bias.
Sir, that not been covered actually in multicollinearity. I should have talked about that, but since time, I did not touch that.
One of the problems that most often we face is a omitted variable bias, and omitted variable bias cannot be estimated the way you estimate multicollinearity or heteroscedasticity by doing test. Most often, what will happen at the end of the day is your results would suffer because of omitted variables, and it is something that you should be aware of by knowing the theory.
Correct. So
yeah,
right.
Yes,
yeah. So thing is that in the suppose there is multicollinearity between variables and you actually omit one variable, and that variable is correlated with the variable that is been included in the model. So if you see this equation for multiple linear regression, if you exclude a particular variable, say x2 from the model, and that excluded variable get captured in the error term, right? So if x2 is correlated with x1 and you exclude x2 from the model, and that will be captured in E1, the error term and the explanatory variable actually gets correlated. And one of the assumption, if you remember, the classical assumption is that xi and ei should be independent of each other. The moment they are correlated, your estimator of beta hat is biased as well as inconsistent, and that is very serious problem in the regression. Okay. I think I did not spend much time on that due to lots of time that we consume for other things. But it is very serious problem when you omit the variable and that variable is actually correlated with the variable that is included in the model, because then your error term and explanatory variable gets correlated. If xi and ei are correlated, the estimator would be biased as well as inconsistent, and that is very serious issue that you must tackle.
Thank you. In fact, there's another issue is incorrect functional form. So we might actually specify it is ultimately regression equation is a functional form you specify. Regression equation is not either the reality or it's a equation that you write which you get evaluated for the beta hats and alpha and whatever. So the functional form that you write, like if the functional form is not linear, or there is, as he while doing VIF, he gave a very nice example of how interaction term would make a difference. So the functional form of the relationship of x set of x with y is an important thing, and that again a theorist should know for themselves. Like they should have a good reason to write that functional form. Often people believe that now we know R and we know a little bit of, we have data. So if we could write a few x's and one y and run an equation, and if we get significant results, it means that x predicts y. That is not going to happen. The best example is, there's a very interesting data of people doing this thing. Making predictions of hair density on the head and incomes. So आपके सर पे ज्यादा बाल है तो आपकी इनकम कम रहेंगे, और आपके सर पे बाल कम है तो आपका इनकम ज्यादा रहेगा. मेरे तरफ मत देखिए. लेकिन ऐसा, if you do this kind of a regression, perhaps it would be absolutely significant. And often this is a spurious relationships, because the hair density is determined by age, which actually causes income. As you grow older, your incomes increase, you become more experienced, and so on and so forth. As you grow older, perhaps you lose more hair on your head. Something else cause. So the simple intuitive example that tell you that significance of beta value is important if your theory is right. Otherwise, any two things you put in equation, you're going to get something. And if you put more things in equation, certainly you will get one of them significant. So the shotgun way of looking at statistical analysis is not the best way. And so many times I've discussed with Bhavesh, and he is one of those people who have this part of this kind of understanding very right in his head. Like otherwise what happens is people learn to do statistics, and then they take data and they run regressions, and they believe that now what we have found is right. But the underlying theory that comes from your own discipline is so very vital. Like otherwise anything that you put, like why not to make y as x and x as y, even that regression is possible with the cross-sectional data.
Yes,
get significant results still. You keep y, and x, because there is a theory that says that x is a cause and y is a effect.
right.
And what is a cause and what is the effect is not something regression will tell you. In the sense, there are ways in which you can infer in some models. Say, for example, you have in time series methods of determining causality. Say, for example, Granger causality model would perhaps in a predefined sense can tell you what causes what, because and for that you need a time series data. Most often social scientists don't deal with a time series data unless and until you are lucky to be an economist, right? Where you actually get a time series data and These are the people who actually have the luxury to deal with time series data. Unfortunately, as a psychologist or as a sociologist, people find it very difficult to get a time series data, and they then end up having one cross-sectional data and try and determine causality, which is quite a uphill task, honestly. Best way is to have a panel data.
Correct.
And those kind of data sets would perhaps help you determine causality. Otherwise, when you have cross-sectional data, the kind of data most social sciences have, I think what we need to do right is our theory. Simply because we run regressions, we get fancy graphs, we get p-values significant, doesn't mean X causes Y. And that's the feeling that we should try and avoid. And Bhavesh is one such young man I really love to talk to, because he has got his theory right and his econometrics is awesome. So personally, as well as on the behalf of my Department of Applied Psychology, on behalf of HRDC, and on behalf of all the participants, I extend warm thanks to Bhavesh.
Thank you, sir.
And Bhavesh, I've been seeing now since perhaps you teach in a university for 20 years. I have seen Bhavesh growing right from being a master's student to a faculty in the department, and he has got some impeccable publications to his credit. He is somebody who, if we casually meet and discuss, would appear very simple and gentle person. But when he sits in his office and talk about economics, you understand how much depth he has gained in his subject. And it's pleasure to have young colleagues like him. And I have always had pleasure to interact with him. In fact, quite a few people from his department, like his advisor, tomorrow she would be talking to you. There is a legacy that his group of researchers is creating. Professor Hattekar, who spoke with us, Professor Patnaik, who is going to speak with us, Vasuprada would talk to us on social network. These guys are creating a legacy of doing quantitative in a correct manner. These are not the people who get happy simply by looking significant p-values. These are people who spend a lot of time in understanding things. And there are a lot of things that I have learned from his department, him personally, and a lot of his colleagues. And I'm glad that I could invite him and he could find time and talk to us. Thank you, Bhavesh. Thanks a lot for coming and talking to us. And we want you to come back and talk to us again and again, because there's a hard work that people do and develop some in-depth understanding, and that is something where you get to learn a lot of things. So I hope this session was useful to everyone, and I thank everyone, and Bhavesh in particular. Thanks, Bhavesh.
Thank you, sir, and thank you for your kind words. They are always encouraging, and I really enjoy, sir, speaking with you in the campus whenever we meet. You talk about time series and all those things. Really, I enjoy that, and I have learned things from you also. The way you put the things in very lucid way. I had attended one of your workshop on structural modeling when I was doing a PhD. I don't know if you remember that, but I remember it very
I
well.
do remember.
Yeah, structural modeling workshop. So that was really, sir, to learn something, how to put the things in a very simple way, sir. So thank you for inviting me, sir. It was a pleasure interacting, and really, I hope that audience will go out with something in their mind when we finish this session. Thank you so much for invitation. Thank you.
Thank you. Thanks a lot, Bhavesh. Thanks for those memories of workshop. But I actually talked to him about time series, honestly, because I don't know and he knows.
No, sir, that's not that. It's not like that, sir. But it was both way. It's benefiting. It's both way. The causality is both way, not the unidirectional.
Okay, he is a scientist. So thanks, people,
Yeah, thank you.
and see you tomorrow. Please log in by 9:55 at least. Because it doesn't look nice that a resource person has joined and we are not there. So try to join early. If your name is not added in one of the groups, one of the 4 groups, Rekha ji, your name is added to group 2. So that I have posted on the group. I have also given data for group 2. Income data is only bivariate data, and since it's a multivariate thing, I have added different data, heart data karke data file, which is for group 2, which is shared on the group. So please use that data file. For rest of the 3 groups, data is already shared with you, so you can start playing with the data. With at least 3 sessions being taken on data analysis, on regressions particularly, and all the data sets that were shared with you have basically some kind of causal models to deal with. So I hope today onwards, at least you can play around with the data, import data, do something, plot graphs, and have fun with the data, because unless you play with the data, you will not be comfortable with the software and things like that. So I hope you will have fun. Thank you very much for joining today.
Sir, Vivek, one
Yeah.
request.
Yeah.
Could you please share the morning your file, the command file which you have?
Yeah, I will share that file.
Okay, so that will be easier now.
I thought I have posted them during my session, so you must have copied, but if you've not copied, I'll
But
share
then
them.
we got stuck at one command and then we cannot execute the other command.
Okay, yeah, I
That's
get
the
it.
issue.
Thank you, madam. So
Yeah.
I will do that. Anything else? Okay, thank you one and all.
Thank you.
See you tomorrow, 9:55. Bye-bye.
Thank you.
Bye, bye, bye.
Thank you,
Thank you, sir. Bye.
Thank you, Bhavesh. Thank you.
Bye, sir.
Thank you. Thank you all.